We know that a white dwarf is the remaining corpse, the degenerate corpse, of a star that's shed all of its outer layers as a planetary nebula. Primarily it's carbon, and it's also some oxygen, depending on the original mass. So there could be some helium capture to produce not just carbon, but also oxygen. And it turns out that the core has a mass about the mass of the sun, approximately. Temperature about 30,000 Kelvin, so very hot. Luminosity about 1/100th the luminosity of the sun. Essentially, you can think of the white dwarf as being stellar in mass, but the size of the Earth. The density is so great when you consider a stellar mass and something the size of the Earth that 1 teaspoon would weigh about 5 tons, like a big truck. So 1 teaspoon, 5 tons. That is pretty amazing. Here is an actual image of a white dwarf along with a companion star. This is actually Sirius, the brightest star in the sky. Sirius A is shown here. That is the brightest star in the sky. This is its companion, Sirius B. It's a white dwarf. Why does it look so bright? Oh, because this is an X-ray image. Notice the image invisible. The brightness roles are reversed. Sirius A is much brighter in the visible than the white dwarf, but much dimmer in the X-ray. That just shows you that the temperature is extremely high. You would expect something that's 30,000 Kelvin to have a maximum wavelength of emission that's much shorter than visible light. You probably have heard the term nova. Well, a nova, turns out, is associated with a white dwarf, so we will call it a white dwarf nova. Now, sometimes white dwarfs are in association with a companion star. So in this artist's conception, we see a red giant that's filled its Roche lobes, and through L1 it's passing some of its gas, which is accreting onto the white dwarf. So hydrogen gas is circling in, which is similar to the accretion disk we see around protostars, the protostellar disks, and that hydrogen accumulates on the surface of the white dwarf. The white dwarf is very dense. Mass of the sun in something the size of Earth, so its gravity is incredible. And it compresses the hydrogen into a very thin, hot layer. When hydrogen reaches 10 million Kelvin, it explodes the hydrogen gas because of fusion. So it is a thermonuclear flash that's known as a nova, which means new star. Now, if you happen to be so lucky to see a new star, you wouldn't really know it's a nova. You wouldn't know what it is because it's really hard to distinguish. You have to do some study. But it turns out that a nova is not a supernova. Rather, a nova explosion is approximately 100,000 times the luminosity of the sun, where a supernova explosion, which we'll learn about shortly, is about 10 billion solar luminosities, which turns out to be about a factor of 100,000 beyond the nova, 10 billion. Here's an example of a nova, Cygni 1975. Here's the progenitor star, and after it went through its hydrogen detonation, producing helium, it lit up to an incredible brightness as seen there. So it turns out that if you explode that hydrogen that's accumulated on the surface of the white dwarf, it doesn't destroy the white dwarf. It can continue to do that as it bleeds gas from the giant star companion and repeat the process over and over. Sometimes the effects of this explosion are visible for years after the fact. You already know that the white dwarf is an odd object. It's a degenerate core about the size of the Earth. Well, it's about the size of the Earth if it's a 1 solar mass white dwarf, but if it's more massive, notice it gets smaller. As the mass increases, gravity can actually compress it, this degenerate material, to a smaller size. The electrons have to move faster and have this tremendous ability to resist the force of gravity, trying to crush it. Now, this is consistent with the helium core, which, as we added material to the core contracted and actually got smaller. Now, this is a graph of the radius of the white dwarf versus the mass. Radius in terms of solar radius, mass in terms of solar mass. Now, this is already small, so there's 1/100th a solar radius, 2/100ths, etc. And the mass compared with the sun, so here's 1 solar mass. This graph does something really strange. You notice, consistent with this graphic up here, that the size of the white dwarf decreases as mass increases. But what happens here just under 1.5 solar masses, specifically 1.4 solar masses? You'll notice the graph showing the size going to 0. Well, what really happens? Something very strange. Now, as the mass goes up, the electron speed has to increase in order to produce the resistance needed. But there's a limit as just how fast you can make electrons go. For instance, they can't exceed the speed of light. So this is consistent with that limit. And what actually happens is that at this 1.4 solar mass, which is known as the Chandrasekhar limit, based on the name given to the person who did the theory, including quantum theory, behind all this, that the white dwarf will actually detonate into what's known as a white dwarf or type 1a supernova, to be discussed next. Under certain conditions, a white dwarf can really get your attention. The accreting white dwarf that is gaining hydrogen gas from its partner, and that hydrogen gas is going into thermonuclear fusion and producing helium ash, right? So there can be a buildup of helium ash with each nova event. So the mass can increase on these white dwarfs. Well, if the white dwarf ever arrives at a mass of 1.4 solar masses, it will be its last. As it approaches the mass, the temperature rises as gravity continues to crush the core down in size. Eventually, it can permit the fusion of carbon. That's 600 million Kelvin temperature required. Now, this is what the white dwarf is made of. It's made of carbon. So when the carbon gets to that fusion temperature, it ignites all at once and produces a carbon bomb of far greater intensity than the helium flash we talked about that took place inside the red giant star, which was extremely luminous. The white dwarf explodes completely as a white dwarf supernova. The entire degenerate solar mass core is completely blown apart. Well, here is the luminosity curve of the white dwarf, supernova, and it's superimposed along with a massive star supernova, which we haven't discussed yet. But this red plot shows the characteristic curve, luminosity in terms of solar units. Notice we're way up here at 10 billion solar luminosities. And then over a period of months, it diminishes down and takes many months to totally disappear from view, assuming it's visible in the first place. So it has a peak luminosity of about 10 billion solar luminosities. The white dwarf supernova ignites at 1.4 solar mass, and since they all do it that way, they have a specific light curve and magnitude. In other words, all the type 1a supernova are essentially the same kind of bomb. So we can discover their intrinsic brightness, which turns out to be an absolute magnitude of about -19. So no matter where they are in the cosmos, when we see one going off, we know how bright they are. That's called a standard candle and very useful for determining cosmic distances to objects we're interested in. Type 1a supernova here is an example that was caught in the act in NGC 4526. Notice that it's a significant fraction of the light of the whole galaxy. maybe about 10% of the light of the parent galaxy that it finds itself in. I thought I probably should own up and confess that everything I've just said about white dwarfs is a lie, because this is a real white dwarf.